Every time you send a transaction on a blockchain, something has to receive it, validate it, and pass it on. That something is a node. Nodes are the actual infrastructure that blockchain networks run on, not servers owned by a company, not data centers controlled by one organization, but thousands of independently operated computers around the world, each maintaining a copy of the chain and enforcing its rules. Understanding what nodes are and how the different types work is the foundation for understanding why blockchain networks are actually decentralized, how that decentralization is maintained, and what trade-offs get made when you optimize for storage, speed, or historical access. What a node actually is. A node is any computer that connects to a blockchain network and participates according to the network's protocol. There's no central server that nodes connect to. They connect to each other. Each node independently verifies transactions and blocks, and the network reaches consensus through agreement across thousands of these independent participants. This architecture is what makes blockchains resistant to single points of failure. If one node goes offline, the network continues. If 1,000 go offline, the network continues. The data exists across every participating node simultaneously, and no single entity controls it. In 2025, Ethereum had over 11,000 active validator nodes globally. Bitcoin's network runs on tens of thousands of full nodes, distributed across more than 100 countries. These numbers represent the actual physical infrastructure, making decentralization real rather than theoretical. Full nodes. A full node downloads and stores the complete blockchain from the genesis block to the present. It independently validates every transaction and every block against the network's consensus rules. It doesn't trust other nodes to tell it what's valid. It checks everything itself. Full nodes are the backbone of any decentralized network. They enforce the rules. When a miner or validator proposes a new block, full nodes check it against the rule set. If it violates any rule, the full node rejects it, regardless of what other nodes say. This is what makes blockchain consensus genuinely trustless. No authority enforces the rules. The rules enforce themselves, because every full node independently applies them. Running an Ethereum full node in 2026 requires meaningful hardware, a 4-core CPU, 16 GB RAM, and a 1 TB NVMe SSD at minimum. The blockchain grows continuously, so storage requirements increase over time. Bitcoin's full node is considerably lighter. Bitcoin Core runs on modest consumer hardware, and the barrier to entry is low enough that running one at home is genuinely accessible, a deliberate design priority in the Bitcoin philosophy. Full nodes do have one important limitation. They store current blockchain state but don't preserve every intermediate state the blockchain passed through to get here. They can tell you the current balance of any address. They can't reconstruct what that balance was at block 9 million. For that, you need an archive node. Archive nodes. An archive node is a full node that keeps everything. Not just the current state, but every historical state the blockchain has ever been in. Every account balance at every block. Every smart contract storage value at every point in history. The complete record back to block 0. This is an enormous amount of data. An Ethereum archive node in 2026 requires 10 terabytes or more of storage. The Ethereum blockchain archive surpassed 3 terabytes by mid-2025 and continues growing. Who actually runs archive nodes? Infrastructure providers, blockchain analytics companies, DeFi protocols, and developers building applications that need historical data. When you use a block explorer like Etherscan to look up a wallet's transaction history, or when a DeFi protocol needs to verify a historical state, they're querying an archive node. Most individual users don't need one. The hardware requirements are substantial, and the use cases are specialized. The distinction from a full node is simple. A full node tells you the current state. An archive node tells you the state at any point in history. Light nodes take the opposite approach. Instead of storing the full blockchain, a light node downloads only block headers, compact summaries of each block, without the actual transaction data. When a light node needs to verify a specific transaction, it uses a cryptographic method called a Merkle proof. The block header contains a hash that mathematically represents every transaction in the block. The light node requests proof from a full node that a specific transaction is included, verifies the math, and confirms the transaction without ever downloading the full data. In practice, light node logic is what runs inside most mobile crypto wallets. When you check your balance or send a transaction from a phone, you're interacting with the blockchain through light node functionality, relying on full nodes for the heavy lifting while doing just enough local verification to maintain security. The trade-off is trust. A light node trusts that the full nodes it queries are honest because it doesn't independently validate every transaction. For most use cases, sending, receiving, checking balances, this is an entirely acceptable trade-off. For applications where independent verification matters, it isn't. Validator nodes. In proof-of-stake networks like Ethereum, validator nodes are full nodes that have staked collateral to earn the right to propose and attest to new blocks. On Ethereum, the minimum stake is 32 ETH. Validators are randomly selected to propose blocks and earn rewards for doing so correctly. Validators who behave dishonestly can have their stake partially or fully destroyed in a process called slashing. Why the distinction matters. The three node types exist because decentralized networks face a fundamental tension between completeness, accessibility, and resources. A network where every participant had to run an archive node would have very few participants. A network where everyone ran light nodes would lose independent verification. Full nodes balance this. Enough data to independently validate everything without the complete historical record that most participants don't need. Light nodes bring accessibility to end users and mobile applications. Archive nodes serve the specialized infrastructure layer, analytics, development, forensics. Together, they form a layered architecture. Archive nodes hold the complete record. Full nodes enforce the rules across thousands of independent participants. Light nodes bring the network to devices that couldn't run a full node. This is one of the reasons blockchain networks can scale their user base without requiring every user to become a full infrastructure participant. The security model doesn't depend on everyone running a full node. It depends on enough people running full nodes that no single entity can control or manipulate the record.